Welcome back. In this video, we are going to go through the combinational logic circuit design process. So we are going to quickly review simplifying a Boolean expression using Boolean theorems and De Morgan's theorems, and go over some more complex examples of why and how we simplify. We're going to describe the sum of products form for a Boolean expression, and then we're going to get into the design process. We're going to learn how to design a digital circuit using simplification techniques such as Boolean theorems and a new technique called K-maps. So first, I'm going to introduce a new term called the sum of products form. It's a Boolean expression that consists of two or more AND terms, or products, or you can think of the symbol of multiplication, that are ORed together. Here is an example of an expression that is written in SOP form. It's a sum of products. So we have groups of products that are summed together. Sum of products form. Keep in mind that for sum of products form, one inversion sign cannot cover more than one variable. So if you've got an overbar that covers more than one variable, you're going to want to apply De Morgan's theorems to break that out so that you only have one inversion sign over one variable. So the methods of logic circuit simplification and design that we're going to go over in this video will require that your logic expression be written in SOP form. So as I refer back to that form, this is the form that we're talking about. There's also a product of sums form, which is the exact opposite. It's two or more OR terms, two or more sums that are ANDed together. Here's some examples of product of sums form. So we have products of groups of things that are summed together. For the purposes of this lecture, we're going to stick with writing things in SOP form, sum of products form. I just wanted to show you product of sums form so that you are aware that it exists. But as we go forward, we're going to stick to SOP form for this video. It may come up from time to time that we discuss POS form, so it's best to know both. But again, for the most part, we're going to stick to SOP form in this video. So in the last video, we talked about Boolean theorems, and we talked about how to use those to simplify a circuit. For example, let's say that you were given a design specification where you have to build the circuit on the left, circuit A. If you can figure out how to simplify that, you might be able to build something much simpler. For example, circuit B is equivalent to circuit A. If you have to wire and test and troubleshoot a circuit, would you rather pick A or B? I think most people would pick B. This is why we try to simplify before we build and test so that we can save ourselves time and money. So the simpler form typically will contain fewer terms and or fewer variables. The simpler form will always be equivalent in operation to the original as long as you have applied the Boolean theorems correctly. The simpler form will always be equivalent to what you started with. And some other benefits of implementing a circuit that has a simpler form: you have less gates, so it's smaller and cheaper to build, less interconnections, less wiring, which means less error that could come from a misplaced wire or some other potential circuit fault. If you have fewer gates, your circuit will operate faster. So there are tons of reasons and benefits to trying to simplify using Boolean theorems or using the tool that we're going to discuss later on in this video, K-maps. So let's practice simplification. On your lecture notes, you have a picture of this circuit. Take a minute, pause the video, and try to simplify it. And in order to do that, you're going to take the output expression right here, apply those theorems that we discussed in the last video, and see if you can get something simpler. Once you do, draw a picture of that simpler circuit. So here's the solution to simplifying this circuit. Here's what we started with originally. And after you apply De Morgan's theorem to that very last term, the in parentheses, you have not A and not C in a NAND gate. So when you break the bar and change the sign, you end up with this term right here. Break the bar, change the sign, you end up with here. Now we do have two double inversions within this term, so we can cancel those out. Next, we can distribute the A and not B to both terms in the parentheses. That will lead us here. Lastly, if you look at the middle term, you have A and not B and A. Well, I know that A and A is just A, so I can really rewrite this as A and not B. Next, we're going to factor out the AC from the first term and the last term. Look at the first term and the last term. Both of those have an A and C. So I'm going to factor the A and C out, leaving a B or not B behind. And then we still have this middle term that is written right here at the end. After I factor out that A and C, I can see that B or not B is equal to 1. That's from one of the theorems that we discussed. That is from Theorem 8. So we're going to use Theorem 8 to then replace the B or not B with a 1. I also know that AC and 1, or anything and 1, is itself. That's Theorem 2. And the last thing that we can do is factor an A out of both of these two terms that are left. When I factor out the A, this is my final expression. And it does not get any simpler than that. So now that I've simplified this expression, I'm going to draw a new picture showing the circuit with the simplified implementation. And here's what I'd have. I have C or not B going into an AND gate with A. So, this is the simplified circuit. This is what we started with. It's very clear at this point why we want to try to simplify. Look at all of the work you can save yourself by simplifying before you try to implement or build a circuit. Let's look at another example. The second example in your notes asks you to simplify the logic circuit shown here. So take a minute, hit pause, and try to simplify this circuit on your own. Start by writing the expression for the output and then go from there trying to simplify it. And here's the solution for this circuit. If we write the expression for the output just based off of how we read or interpret the circuit, you'd get not A or B and A or not B. You can then use Theorem 13 to multiply or FOIL that out in order to get this expression here. Next, you can use Theorem 4 to simplify the first term and the last term. Those both end up being 0. So now we're here with this expression right here. There's not really anything else you can do to simplify this expression, so that's your simplified expression based off of what we started with. If you were to draw a circuit for this expression, you would get the circuit right here on the left. This is what we started with. This is what we got after we simplified. And if you look at it, it doesn't really seem too much simpler. The first circuit has 2 OR gates and 1 AND gate. Second circuit has 2 AND gates and 1 OR gate. Not that much different. They both have 2 inverters. Not that much different. So we can see that both circuits contain the same number of gates and connections. In this case, the simplification process produced an equivalent but not simpler circuit. So there are times when you may attempt to simplify and it just can't get any simpler, and that's okay. But we always attempt to simplify because you never know what might come out, and it may end up being something much, much, much simpler than what you started with. So sometimes we can't make it simpler, but we always attempt because the benefits outweigh the costs of trying to simplify. we're going to go forward and talk about the design process a little bit more. But before we can do that, we have to learn a new skill. And that skill is to write an SOP term from a truth table. Remember, SOP means sum of products. So if you flip to the second page of your notes, there are some examples where I'll show you what writing an SOP term means. It's actually quite simple. When you have a truth table, like this one shown here, you'll have your inputs set up as usual, and then you'll have your outputs. When you write an SOP term from a truth table, you're simply going to start by identifying all the rows where the output is 1. Start by identifying all the rows where the output is 1. Then you're going to write a term to describe that output based off of the inputs. The term for this row would be not A and not B and C. Basically, you're going to write the variable names A, B, and C, and if that particular variable in that row had a 0, you invert that variable in the output. So for the next one, A is a 0 here, so the output here is not A and B and C. For the next one, we have B and C are 0, so the output here is A and not B and C. Once you get all your SOP terms, you're simply going to write an SOP expression, sum of products. You're going to add those all together using the OR operator. And this is going to be the expression for the output. So you take each term, put an OR in between each term. That's the expression for the output. That's how we write SOP terms from a truth table. Let's look at another example. In this example, we have a similar truth table. We're going to identify all the rows where the output is 1. And then we're going to write the terms for each row where the output is 1. This one will be not A and not B and C because they're all 0. This one will be not A and not B and C because the first two are 0 and the last one is 1, and so forth. Next term would be not A and B and C. The next one will be A and B and not C. And the last one will be A and B and C because they're all 1. Then you're going to take those terms and write an expression for the output. And that expression is just going to be a sum where you sum all of the products. Let's take a look at one more example where now you have a truth table with 16 rows. You're still going to apply the same process. Identify all the rows where the output is 1. That's where they are. And now you have 4 variables instead of 3. Other than that, you're going to apply the same process where you write the terms based on the inputs. We have 0, 1, 0, 0 here. So we have not A, B, not C, not D. And you're going to continue to apply that same process to each output that is high. Don't forget, when you're done, you have to write the final expression for the output by summing all of those terms together. So this tool of writing an SOP term from a table is going to be useful when we talk about designing a circuit. And that's what we're going to do next, is design a circuit based off of a specification. Now here's our basic design procedure. You're going to interpret the problem and set up a truth table to describe its operation. So you'll get a problem statement. The problem statement will tell you everything you need to know about that circuit, what the inputs will be, what the output should be based on the inputs, etc. And based on that, you're going to create a truth table to describe how that circuit is supposed to work. Then you're going to write the AND or the product term for each case where the output is 1 and write the SOP expression for the output. That's what we just practiced on the last examples. After you write your SOP expression, then you will simplify it. That's why we spent so much time talking about simplification and Boolean theorems. Because when you design a circuit, once you get that SOP expression, the next step is to simplify it if possible before you actually implement the circuit or build the circuit and test it out. So this is our basic design procedure, and I'm going to show you through an example how we apply it. So flip to the next page in the notes, and it says, design a logic circuit with 3 inputs, A, B, and C. The output should only be high when a majority of the inputs are high. Now, majority of the inputs are high, so that's going to be important. So based on the problem statement, we know we have 3 inputs. We know that the output will be high only when a majority of the inputs are high. So if you only have 3 inputs, that means when 2 or more inputs are high, the output would be high. So we're going to set up a truth table to describe that. According to the directions, or according to the problem statement, the output is only high when 2 or more inputs are high. I've just highlighted the places where that happens. So when you set up your truth table, remember the inputs are set up the same way every time. Follow the pattern we discussed in a prior video. The output you're going to fill in based on the statement. So based on the statement, we can see that the output will be high when B and C are both high, when A and C are high, when A and B are high, or when all 3 are high. Those are the only times we'll have a 1. And from there, you're going to write the expression of the output based on your product terms. So here are your product terms for each row. And now you're going to write a sum of products expression using those 4 pieces from your truth table. Here's your sum of products expression for the output of that circuit. So if we can build a circuit that implements this expression, we've designed the circuit in question. But before we go and build that specific expression, we're going to simplify it first. So let's take a look at how we would do that. So there are several ways to attack this particular problem in terms of how to simplify it. The quickest way is to realize that the last term, A and B and C, has 2 variables in common with each of the other terms. We can use the ABC term to factor with each of the other terms. So here's our expression. And what they've done here is simply written out the ABC in front or at the end of each term. So we have an ABC here, an ABC here, an ABC here, only because it makes it easy to see that the B and C can be factored out of these 2. The A and C can be factored out of these 2. And then the A and B can be factored out of these 2. So if you read the description here, it says the expression is rewritten with the ABC term occurring 3 times, and this is legal in Boolean algebra because ABC or ABC is itself. You can rewrite that term as many times as you want. So the reason why it's shown 3 times is to clarify how we can factor later. So we have this ABC term written a few extra times, and then we're going to factor. So out of the first 2 terms, we're going to factor out a BC. Out of the second 2 terms, we're going to factor out the AC. And out of the last 2 terms, we're going to factor out an AB. We can look at our theorems, and we can see according to theorem 8, that's going to be 1, that's going to be 1, that's going to be 1. And this simplifies down to this final expression here. That's the expression for the output of our circuit, and that's the circuit we're going to build. We're not going to build a circuit based off of this. This is more complicated than the simplified version. This is the circuit that we're going to now build. And there's our image showing how that circuit would look based off of the expression we got when we simplified. So now we're putting a lot of pieces together that we've discussed since the beginning of the course. Implementing a circuit from an expression, simplification, Boolean theorems, all of these things come together for the design process. And that's how we would apply that process. Let's take a look at another example. So flip the page in your notes. Refer to the figure below where an analog to digital converter. I'll stop right there. If you don't know what an analog to digital converter, it is a device that takes an analog measurement, maybe temperature, voltage, current, things of that nature. It converts it to a digital output, ones and zeros. Okay, so if you use a thermostat in your house, you're using an analog to digital converter every day when you turn the AC on and tell it what temperature you want it to be in your house. That your air conditioning system takes a measurement, that's an analog value, it measures the temperature of the room, converts it to a digital equivalent, and uses that to begin your process of cooling down your house until it gets to the temperature you selected. So an analog to digital converter is monitoring the DC voltage of a 12-volt storage battery on an orbiting spaceship. So we have a device that's monitoring a voltage level. That's your analog input. So it's monitoring the voltage level and giving you a digital number that tells you how much voltage is left in the battery. The converter's output is a 4-bit binary number, ABCD, corresponding to the battery voltage in steps of 1 volt, with A as the most significant bit. So for example, if the output of the converter is 1000, that would mean in decimal 1000 would be 8. That means the battery has a voltage of 8 volts at this point in time. The converter's binary outputs are fed to a logic circuit that is to produce a high output as long as the binary value is greater than 0110, which is 6 in decimal. So as long as the battery has 6 volts or higher, no, actually, as long as the battery voltage is greater than 6 volts, so 7 volts or higher, then you're going to have an output of high from your circuit. If the battery voltage is 6 volts or lower, the output will be low. So now we're going to design the circuit. We're going to start by taking all of this information and transferring it into a truth table. So you know from the problem description that you have a 4-bit number going into the circuit. So you have 4 inputs. So you have a truth table that needs 16 rows. And based on the problem statement, it said that the circuit is to produce a high as long as the binary value is greater than 0110. Here's where 0110 occurs. So every binary value after this is going to be greater than 6 because your inputs to your truth table are counting up in binary. So for every input after 0110, you're going to have a 1 at the output. Anything that's 6 or below is going to be a 0 at the output. So first step, very important step, we have to be able to translate what the problem is describing into a truth table. We can't design without a truth table. You have to be able to translate what the problem is describing into the truth table. So I believe we have captured that, because we have a truth table that will produce a 1 anytime the binary input is greater than 6. Now we have to write our sum of products expression. But notice how many SOP terms we would have. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 terms in our sum of products expression, and each term has 4 variables. That would be long and complicated to simplify using Boolean algebra alone. So we need another tool to be able to solve this. That's where K-map comes in. K-map is short for the word Karnow map. Karnow is the last name of the person who discovered this method. It's a graphical method of solving logic equations or solving a truth table. Theoretically, it can be used for any number of variables, but we won't use it for more than 5 or 6 variables. Actually, with the examples that we have from the textbook in this class, we won't go with more than 4 variables. A K-map is a graphical representation of a truth table. It's another way to represent a truth table. So let's say that this is the truth table you've been given. A K-map is a graphical representation of the same exact truth table. If you have 4 rows in your truth table, you'll have 4 squares in your K-map. We label the squares with like a coordinate system. And you'll follow both a row and a column to get to a specific point. So for example, we know that the output when A is 0 and B is 0 is a 1. We know the term for that output will be not A and not B. When you make your when you make your K-map, you'll draw a square, you'll label the rows and the columns, and you'll look for the same coordinates. Wherever those two coordinates meet is where the output goes. So for this column right here, 0 and a 1 give you 0. That would be not A and B. So not A and B meet right here. The 0 goes there. So the K-map is a way to graphically represent a truth table. This is one for 2 inputs. If you have 3 inputs, you'll have a rectangle with 8 squares. And every 1 in the truth table will correspond to a 1 on the K-map. And how we set up this K-map, or how we fill it in, is based off of a coordinate system. So this is one coordinate and this is another coordinate. So for example, not A and not B and not C corresponds to the first row of the truth table. So we know that the 1 in this output goes here based on the idea of a coordinate system. Here's a K-map for 4 inputs. If you have 4 inputs, you'll have 16 rows in your table, you'll have 16 cells in your K-map. And again, every 1 from your K-map corresponds to a specific 1 in the, every 1 on your truth table corresponds to a specific 1 in your K-map and a very specific place. So the first thing that we're going to practice is how to create a K-map. Look on your notes on the page that says creating a K-map. There are some examples and we're going to practice creating the K-map together. The first example has 8 rows. So you're going to draw a rectangle with 8 cells in it. 8 cells. And on the outside of the rectangle, you're going to label it exactly as I have labeled mine. On the vertical side, you're going to put the first 2 variables. And you're going to call it A prime, B prime. And below that, you're going to write 0, 0. The next row will be A prime B. And below that, you're going to write 0, 1. The next one will be AB. And below that, you're going to write 1, 1. The next one will be AB prime. And below that, you're going to write 1, 0. That's how you fill in the column here. Across the top, you'll label this row with not C, and below that, write a 0, and C. Below that, write a 1. So before you filled in any of your squares, you're going to label your K-map this way. It's very important that you label it this way. This labeling system will help you to fill in the K-map and then help you to figure out what to do with the K-map when we discuss how to get the output from it later. The numbers here are going to easily help you identify where the output goes. So look here, this is 0, 0, 0. So you're going to find 0, 0, 0. And where these 2 squares meet is where the output goes. So this one goes here because this is the coordinate 0, 0, 0. The next row is 0, 0, 1. And that has a 0 as the output. So you're going to go find 0, 0, and then find 1. And that cell right there is where the output goes. Next, you're going to go find 0, 1, 0. 0, 1, and 0. Those 2 meet right here. So your output goes there. Next, you're going to go find 0, 1, 1. 0, 1, 1. Those 2 meet right here. 0, 1, 1. So your output goes there. Now, you may be very tempted to just continue filling this in by putting the next value here, but that would not be correct. Take a look at the labeling. Your next row, from your truth table is 1, 0, 0. But where is 1, 0, 0 on the K-map? It's not right here. 1, 0, 0 is down here. So it does not just get filled in top to bottom. 1, 0, 1 would be here. And then this cell right here is 1, 1, 0. 1, 1, 0. So you're going to go to 1, 1, 0. You see there's a 1 there. You find that cell on your map, 1, 1, 0. Fill it in. That's how we create the K-map. We haven't talked about what to do with it. Right now, we're just talking about how do I make one? That's the only thing we're focusing on right now. How do I make a K-map? So if you have 3 inputs, your K-map will look like this. You'll label it on the side the way I've shown you here, and then you'll fill in the outputs like I showed you. Let's do another example. Here's the truth table. We're just going to create the K-map. Again, you'll start with 8 cells, and then you'll label them just like I've shown you here. Exactly the same as I've shown you here. First 2 variables go along the vertical side. The third variable goes along the top. You want these numbers on the bottom because it very clearly shows you the coordinate system for how to fill in the K-map. And then you're going to fill in the outputs one by one using these as a coordinate system. 0, 0, 0 would be right here. 0, 0, 0. 0, 0, 1 is here. And you're going to take the output from that column and put it right there. 0, 1, 0, 0, 1, 0 would be right there. And then 0, 1, 1 would be right next to it. 1, 0, 0 is all the way at the bottom left. 1, 0, 0 right here. 1, 0, 1 is right next door. And right here we have 1, 1, 0. That's this row in the truth table. Becomes this cell in the K-map. And 1, 1, 1. That's our K-map. That's if you have 3 inputs. Flip the page, and now we're going to do one for 4 inputs. The idea is similar, except along the top, you now have 2 variables just like you do along the side. And the labeling stays the same. A prime, B prime, 0, 0. A prime, B, 0, 1. AB, 1, 1. AB prime, 1, 0. Across the top, you're going to have your other 2 variables. C prime, D prime, that's a 0, 0. C prime D is 0, 1. CD is 1, 1. CD prime is 1, 0. So if you have 4 inputs, you're going to start your K-map like this, where you're going to draw a table of 16 cells and then label the outsides the way I'm showing. Exact same way. And the reason why we label it this way is because the numbers give you your coordinates for where each output goes. The first output comes from that row, 0, 0, 0, 0. So you're going to find 0, 0, 0, 0, and you're going to put the output right there. That output is a 1. The next one is 0, 0, 0, 1. That's right there. Now, if you're not paying attention, you might be tempted to put the next output right here, but that would be incorrect. Okay. So we've done 0, 0, 0, 0 and 0, 0, 0, 1. The next one in line is 0, 0, 1, 0. Where is that? 0, 0. 1, 0 is right here, so it doesn't necessarily go in order. You have to pay attention as you fill it in. 0, 0, 1, 1 is right here. 0, 0, 1, 1, 0, 0, 1, 1 goes here. And then you'll continue to fill it in based off of those coordinates. 0, 1, 0, 0 is here. 0, 1, 0, 1 is here. 0, 1, 1, 0 is here. 0, 1, 1, 1 is here. Again, you may think I'm just going to go to the third row and continue filling this in. That would be incorrect. If you're going to fill in 1, 0, 0, 0, where is that cell? 1, 0, 0, 0 is down here if you look at the coordinates. It's not the next one in line. So you just have to be careful as you fill this in that you pay attention to each coordinate cell and make sure you find the right cell on the K-map as you're filling it in. So if you continue to fill in this one, this is what you'll have. Remember, follow the inputs like a coordinate system. 1, 1, 0, 0. Use the coordinates here to figure out where that would be. Find that cell and then fill it in with the output that's listed. We'll do one more. Go ahead and pause the video. Try to do this one on your own. Fill in the K-map based on the truth table given. Create it, label the sides like I've shown you, and then fill in the outputs based off of the coordinates. All right, here is the solution to this K-map. So you should have all of your 0s and 1s in the same spot that I have mine in. And again, you're going to create the K-map with the labeling I have on the side, and then fill in the outputs one by one based off of using the inputs as a coordinate. Now let's talk about what to do with the K-map. Once you've created it, now what? What do I do? How does it help me with the design process? So, once the K-map has been created, you're going to look for groups of 1s to circle. Groups of 1s can be a group of 2, a group of 4, a group of 8, or a group of 16. No other groups. No groups of 6. No groups of 12. No groups of 3 or 7. It must be 2, 4, 8, or 16. 2, 4, 8, or 16. Powers of 2. The 1s must be adjacent to be considered a group. Adjacent could include ones that are on the top and bottom or the right and left side. I'll show you some examples of that in a second. Every one on the map must be circled. Some ones can be circled more than once. And you're going to try to make the biggest circles possible. A group of 4 1s is better than a group of 2. Once all the 1s have been circled, you're going to write the SOP term for each circle on the map. The SOP term will contain any input that is common among every one in your circle. That's very important. I'll come back to that when I show you the examples, but once you make your circles, you're looking for what every single one has in common within that circle. That becomes your SOP term. When you're done, your output expression will be a sum of your SOP terms. If you follow all of these rules correctly, a K-map will provide a simplified expression for the output of any circuit without using Boolean algebra at all. There are a few small exceptions to this that we'll see later, but in general, what comes out of a K-map is 100% as simple as it could possibly be without using any Boolean algebra at all. So now let's look at how we would do some circling. Here's some examples of where you might make a circle. For example, there are 2 1s right here. Here's my circle. When I figure out what the expression for this circle is going to be, I'm going to look at what do both 1s have in common. Both 1s have a B. Both 1s have a not C. So the expression for this circle is B and not C. You're just looking for whatever they have in common. A group can also be top and bottom. Top and bottom. And again, what do both the top and the bottom have? They both have a not B. They both have a not C. So the output expression for that circle would be B, not B, and not C. Another example of circles here. Both of these 1s have the not A and the B, and they have nothing in common here. So my output for this circle would be not A and B. This one, this particular K-map, we have two groups of ones. A group here. And with this group, both ones have not A, both ones have not B, both ones have a C. So the expression for that one would be not A and not B and C. Remember, we can do corners. We can do 2 corners, or we can do 4 corners. They make a group. So this is a group of corners. What did they both have in common? They both have A and not B, and they both have not D. So the expression here is A and not B and not D. Here's some other examples of circles. A group of 4 here. The only thing all 4 of these have in common is C. You look on the left-hand side here, they don't all have an A, they don't all have a not A, they don't all have a B, they don't all have a not B. The only thing they all have is a C. So we would say the output here is C. With this group of ones, the only thing they all have is an A and B. That's it, nothing else. With this group of ones here, they all have a B. They all have a D. So the output is B and D. Remember, we can do left to right, top to bottom. So this makes a group of 4. What do they all have in common? They all have an A. And they all have a not D. And then you can also do 4 corners. What do all 4 corners have in common? They all have a not B. They all have a not D. So there's the expression. That's how we make circles. If you have groups of 8, here's a group of 8. They only have one thing in common. They all have a B. That's it. Here's another group of 8 where the only thing they all have in common is not C. Another group of 8 may be side to side or top to bottom. And again, once you make that circle, you're just looking for what term do all of the ones in my circle have in common, and write those terms out. So now let's practice. Flip the page in your notes, and we're going to practice making circles. Remember, you want to try to make the biggest circles possible. You want to look top and bottom, side to side, 4 corners. Groups of 4 are better than groups of 2, and you have to circle every single one on your map. So, there's a circle there, and then there's a circle there, top and bottom. This makes a group of 4. When we look at what this group has in common, both ones have an A and a B. Both ones have a C. So we write all the terms that are in common, A and B and C. This group, top and bottom, both groups have a B prime and a D. So that's my terms. When I'm done with my terms, I write the output as an expression where I have to sum them all together, add them all up. Let's do another example. Try to identify your biggest groups of ones that you can make. Biggest groups, the bigger the better. So you may be tempted to do a circle of 2 here, but why do a circle of 2 here when you can do a circle of 4? 4 is better than 2. The bigger your circuit is, the simpler the circuit becomes. So here's my groups. There's a group of 4, a group of 4, a group of 4. It's much better to make this a group of 4 than it is to just make this a group of 2. You can circle a 1 more than once. So do that if it helps you make a bigger group. For this circle, the only thing all four have in common is A prime, B prime. They don't all have a C, they don't all have a D, they don't all have a C prime, they don't all have a D prime. The only thing they all have is A prime, B prime. For this circle, the only thing they all have is C, D prime. For this circle, the only thing they all have in common is B, right here, and D prime. When you're done, write your output expression as an SOP term. Here's a third example. Group of 4, group of 2, 4 corners. If you got one in each corner, that's a group of 4. And then this one here can't be a group of anything, but you have to circle every one on the K-map. So that's just a group of 1. If you can't make it a group of 2, it's a group of 1. You have to circle every one on the map. For this group of 2, the term is A, B, C prime. For the group of 4 here, they all have in common an A and a D prime. For the 4 corners, they all have B prime, they all have D prime. And for the one little circle by itself, it's got A prime and B and C and D. Notice that if I only circle 1, 1, I've got 4 variables in my answer. If I circle 2 1s, I have 3 variables in my answer. If I circle 4 1s, I have 2 variables in my answer. The less variables I have, the simpler it is. That's why we make bigger circles whenever possible. The bigger the circle, the simpler your circuit when you're done. There's the expression for my output. Turn the page. I'm going to do some more K-map examples where you only have 3 inputs. So if you only have 3 inputs and your K-map looks like this, you can do a group of 4 with top and bottom. And that simplifies to B prime. So the output of this circuit is equal to B prime. That's it. All you need is an inverter. With the next one, if all of your cells on your K-map, if they're all 1, if you can circle everything on the map, your output is 1. It means the output is always high no matter what the input is. Your output is always 1. That's if you can circle every single cell on the map. In this example, we've got top and bottom on the left. We've got a group of 2 at the top left. And then we just have a group of 1. This one here can't be grouped with anything else. So here is our terms. Your group of 1 is going to have all 3 terms. And then we sum them all together. So we've just practiced circling 1s on the K-map. Go back to the first few examples we did for creating a K-map. Should be on page 5 and 6 of your notes. And now go and circle the groups of 1s and write the expression. We've already created the K-map. Go back and circle those groups of 1s. Write the expression. So hit pause. Go back to those examples we started with on pages 5 and 6. And make the circles. Write the output expression. And then check back in for the answer. So here's the solutions to those K-maps in the beginning. Pages 5 and 6, you should have gone back and made your circles and gotten the same outputs that I did. If you did not get the outputs you see on the screen, go back and check your circles again. They might not have been big enough, or they might have had the wrong number of 1s, or you might have just misread what the output is. But you should be practicing how to create a K-map and then read outputs from the K-map based off of this process. The last thing we're going to talk about with K-maps are don't care conditions. Some logic circuits can be designed so that there are certain input conditions for which we don't care what the output is. Could be 0, could be 1, we don't care. Maybe we don't care what the output is after a certain point or before a certain point. Whenever you have a don't care situation, you're just going to place an X in the truth table and in the K-map where the don't care would be, and we treat it as a 1 if it's beneficial, which basically means you can treat a don't care as a 1 if it can help you make a larger group. You don't have to circle only don't cares. You don't have to circle all of the don't cares. You only use a don't care if it helps you make a bigger circle. If not, leave it alone because you don't care what it is. So here's an example. Let's say that we have a truth table like the one shown on the screen, and I don't care what happens if B and C are high while A is low, and I don't care what happens if A is high while B and C are low. I literally don't care. Could be 0, could be 1, it doesn't matter. If you have a don't care, when you create your truth table and your K-map, your don't cares are going to go in, just like a 0 or a 1. So when you have 0, 0, 0, 1, 1, 0, 1, 1 is here. There's your don't care. Same thing for 1, 0, 0. There's your don't care. Now when you make your circles, you still have to circle every 1 on the map. You don't have to circle every don't care. Only use it if it helps you make a bigger circle of 1s. So there's my circle. Without the don't care, I'd have to do a circle here and then a circle here. But with the don't care, I get one big group of 4. That's better than a group of 2, so I'm going to circle it. I don't need to circle this don't care because it doesn't help me make a bigger group of 1s. I've already circled every 1 on the map. I don't need any more circles. So I'm just going to ignore the other don't care. I don't need it. It doesn't help me get a bigger circle, so I'm going to ignore it. And your output is just A. Because A is what all 4 of these squares have in common. So that's how you would use a don't care. Don't cares are nice because it helps to make your circuit even simpler. You get bigger groups of circles, which means you have bigger, more simpler output expressions. So don't cares are a great tool to use when you can use them.